Alright guys, this is unit number 8, lesson 3, and today we're going to talk about shifted forms of the parabola. So we're going to graph them and look for relationships and see if we can find patterns on how they are shifting around the axis. So we're going to just do a little basic review without using your calculator, and really do this because we want to see if you understand how to do these on your own. It's kind of cheating if you do. Sketch the parabola shown below on a set of axes. Just draw your own rough axis. Get up a table and try to, graph some parabola, something like that. So use it. You could generate a table without your calculator because these are easy. So hit pause and try that now, please. All right, let's see how you did with these. And did you get a parabola looking like these? And hopefully, again, yours is roughly like this. The main thing is, do you have your turning point down here? And you have your turning point right there, and it again should look close to these. We know that this is a happy parabola, so it should be smiling. And this is a sad parabola, so it's frowning. So you guys should know that already. But we're looking at something else. Notice that when our parabola is in this form, when there's no B or C, then just an A term, their turning point is always where? Because it didn't matter if we changed this or this, made it positive or negative, the turning point was still right at the origin, 0, 0, and that's important to know. So anytime you graph a parabola in the form of just ax squared, no b term, no c term, it will always be centered right in the middle. Okay, let's keep going. So that's one thing we could observe. This next one's going to teach us some other stuff because look at this big fancy form. Now this is still a polynomial. So you should know that if we multiplied this out, that would give us a trinomial, and you guys could do that quickly. It would be something like x squared minus 4x plus 4. And then you'd just have to minus the 4 there, and then it would end up canceling out, and you just have a binomial, which is still a polynomial. So they just look a little different, but we would be able to multiply this out and graph it. Alright, so now we're going to see if we can find some more patterns. So here is, this is called the parent function. I'll talk about this in class of quadratics. This is the most basic quadratic you can have. And then here's a more complex one. So we have f of x, function f, function g. The graph of f of x is x squared, which is shown here. So here, just like we said, that this is no b or c term, so it's going to be function right in here. And their coefficient's 1. Okay, use your graphing calculator. Now you can actually graph use your graphing calculator, come up with a table, and go ahead and graph this one right on the same axis down here. And then once you do that, I want you to answer question B if you can. How would you need to shift f of x to get it to g of x? So I want you to think of that. So hit pause, try A and B right now. All right, let's see how you did on these. So did your g of x come out looking something, if I can get there we go, something like that. So that's what you came up with. And so we wanted to ask, how could you get the f of x function, this one, onto the g of x function? So did you answer question B, and did you say something like this, maybe? It's supposed to be there. I'll just do that. Let's get this out of the way. Oh, it doesn't want to leave. So you would need to move it 2 units to the right. You can see if I took this and went 1, 2, and then 4 units down, 1, 2, 3, 4. They would map right onto each other. I could have done something like this. That's pretty ugly, but you know what I'm doing here, hopefully. So I could go 1, 2, 1, 2, 3, 4, and it should fit right on there if I had good coloring skills. All right, now what is the turning point of g of x? Where do you see the turning point in the function's equation? So look at the turning point of g of x, and then look at the equation of g of x, and do you see some type of relationship? So hit pause and answer that now. All right, so did you look at the equation, and maybe you saw something like this, if it's there. So here was the original function, and notice that, where's the turning point? It's supposed to be in here, I think. Oh, my graphics aren't working so well today. There it is. So that was the turning point. And you could see that this 2, the negative 2, is really close to there, and the negative 4 is there. So there is a relationship between these numbers here and the turning point, and we'll see that quite a bit. Notice that the 2 is opposite, but the 4 was the same signs.
Aliens are going to take over the world.
All right, so we're going to keep looking for some patterns. So here's our next exercise. Again, this is what we call the parent function of quadratics. And here is a couple other ones. We have this one, and we have this one. And noticing what they're doing to the parent function is they're just adding 2 to it, and they're subtracting 4 to it. So again, using your calculator, we want you to sketch the 2 quadratics and label them. So put the label, the equation next to each graph so we could just determine which one's which. So let's just do part A first. So hit pause and try that now. All right, let's see how you did with these quadratics. So did you get something like this? Okay, so you can see that we have them labeled. The the plus 2 is this one here, and the minus 4 is this one here.
Wow, math is awesome.
What was the effect of adding a constant to the overall function? So what happened when we added a constant? And this is considered adding negative 4. So what did you notice when we added 2 and we added negative 4? Well, hopefully you saw something like this. It shifts up for addition and down for subtraction. And you can see that again, see if I could do a better tracing job here. Not really, but it's a little better. So when I take this function plus 2, I just went 1, 2. And then when we did the minus 4, we just went 1, 2, 3, 4. But you can see it's the exact same parabola. The only thing changing is it's shifting up or down based off these numbers here. All right, so now we want you to state the turning point of each parabola, the new ones. So go ahead and do that for part C. That should be easy. All right, so this one had a turning point of 0, 2, and this one had a turning point of 0, negative 4, which is in the pattern of this last one when we talked about this here. Okay, this time the minus 4 was right there, was still in the turning point. We're just adding plus 0 to this guy in the middle here, so that we're really doing nothing to this on the next one. So notice that, let's bring all this stuff up here, that we're doing like plus or minus 0 to that. That's why this is 0, the 2, 0, negative 4. So hopefully those are patterns we're seeing. Now what would the coordinates of the turning point of the parabola this be? So what would this turning point be? That should be easy now. So go ahead and try that. And you would get something like that. All right, so let's move on. And we got one final exercise here. Let's see about the number of added or subtracted from the input variable before even being squared. Sorry, my daughter's flossing in front of me and she's trying to make me laugh. All right, so this is our parent function, and this is, look, we're taking the x, and before the square, we're increasing the input value by 3. So x plus 3. Here we're decreasing the input value by a negative 1 there. So again, using your calculator, let's go ahead and sketch both of these and label both of them on the grid here. So do that now, please. All right, let's see. So did you graph them something like this? And hopefully you definitely could see the pattern going on here. Plus 3. What happened to that one? Well, look, we took and just shifted it 1, 2, 3, and there's that one there. And then we took this minus 1 and it shifted it to the right here, and that's that one there. All right, so why is horizontal shifting counterintuitive? And did you notice the reason is basically it's supposed to be here. What's going on? All right, sorry about that. I found it. It says the horizontal shift is counterintuitive because subtraction shifts the curve to the right and addition shifts the curve to the left. So remember that when you see the inside the parentheses here, that these ones are opposite, and the ones that were outside the parentheses here, these were exactly the same. Remember, this shifted it up 2 and this shifted down 4. So that's something you're just going to have to get down. And part C should be easy. So let's state the coordinates of those turning points that we already graphed. So hit pause and try that now. right, how'd you do? This one obviously is, whoops, wasn't supposed to do that. This one here is 0, -3. And this one here is, when I said 0, -3, I should have said -3, 0. And,
like pigs.
and this one here is 1, 0. All right, and here we go. Last part. Determine the coordinates of the turning point for each of the quadratics. Note the value of A.
Pigs are going to take over the world.
All right, she's trying to make me laugh. All right, and hit pause and give that a try now. Okay, so how'd you do? This one here, 8, remember, opposite, 8, positive 8, positive 5, because we're doing opposite. So this should be -1, -4. And do you think this had anything to do with it? And it doesn't. Remember, this just keeps it right in the center. So when that leading coefficient was a number, I just kept it right there. But then this stuff would start shifting it. So it still doesn't affect it. So you learned how to shift parabolas. Hopefully that went okay. And we'll practice more of this in class tomorrow.